This tutorial is about MATLAB function ode23, and 2 means it's a second order implementation of Runge-Kutta method, and 3 means that it is accurate to third power of the time interval. So we get an accuracy of delta x to the power 3 or delta t to the power 3. So and so if we implement this for the free fall problem, let's change let's run it only for 4 time units at 0.1 interval, and let's see. Let's look at the velocity profile in this case. So now if I plot the time as a function of velocity as a function of time, and let's plot this as blue dots. And so what we have is that the initial velocity is 7, and then as time progresses, the velocity goes down to 0, and then it changes direction, and then it continues to increase in the downward direction, as we saw in the animation or visualization. So we can do the same solution by much faster method. First of all, we define the function. So we know that our function is mg. So dy over dx is some function. This is the slope function. So the slope function in our case is mg. So first of all, we put that function, that the function of t and v is m times g. So you have seen this before. M, we already know m is 1 and g is minus 9.8. And then ode23, if you look at the help of ode23, you will see that its most simplest implementation is you provide the function, which is the slope function. You tell it over what interval you want to determine it. So in our case, it's t0 to 2tn, 0 to 4 seconds. And then you give it the initial value of the function, which is v0 in our case, which is 7 meters per second. So the output of this is the function at points tb, the values of the function at various points tb. And if you see an interesting thing, it's not asking us for delta t, and that's why it's an implementation where it determines by itself what should be the interval dt to get a reasonable estimate of the function. So let's implement this, and you can see that if you look at the size of TB, it found 13 points for us. So it found that, hey, it's reasonable to just give us 13 points, and if needed it will probably give us more points, but it found 13 points and the corresponding values of the velocity at these 13 points. Okay, and now you can already see that they are similar, but what we can do is we can do a hold on and plot these values as red dots, and then hold off, and you can see it's pretty reasonably estimated the way we had it estimated before. We can also do a similar implementation for the exponential curve. So in case of exponential curve, if we go back here, our function is lambda p. So let's clear CLC, CLF. So let's define function of time and p, and this is minus 2 times p, or let's put lambda times p. And of course we haven't defined lambda yet, so let's go over here and say lambda is equal to minus 2. So that's our function. Okay. And now we can run ode3. We can say, well, find me at some specific points TB and PB and do ode23, and I'm going to give you the function, which is my slope function f, and then my span over which I want you to do this is 0 to 2, and I want you to use the initial value of 1000 as we did earlier. And if we plot this, TB, BB, you see, PB, we get our exponential curve. Now we can also find the exact values at exactly these points, and we know that is 1000 times the exponent of lambda times TB. So this will basically give us the PE values, and now I can put those, so this can stay as a straight line, and then my exact values at these intervals can also be put as TB, PE as green axis. And you can see the ode23 implementation gave us pretty much exact values that you would have expected, because this is a second order implementation and the results are much more accurate. So this is how you can use built-in MATLAB function ode23 to solve a differential equation.